All right. Yeah. So as we had a bit of time today, and Markus had a preprint fitting right in the middle of what we do in the center, something with manifolds and geometry and topology and things.
Not so much geometry.
Not so much. Could be, you know, the geometers, you know, it's your time to go in and fill in the geometry. So yeah, so Markus will give a longer presentation. So classification of certain 4 manifolds in a paper called something with fundamental groups.
Yeah, okay, so Natalie asked me to talk about this paper, but I do want to take some time and just say a couple of things about what could it mean to classify manifolds. There are, I mean, many different things you could mean with that, different approaches of how you could tackle it. And then at the end, I will maybe also say something about what we concretely do and maybe even what the general sort of approaches that we take in this particular thing. I do want to mention that I'm not really an expert on classification of manifolds, so take everything I say with a grain of salt. It's sort of my interpretation of the situation. But here's a basic question I think that is reasonable to ask once we, you know, let me do the Dustin move and say, let's just assume that we care about manifolds and sort of how they look and how we can understand them. So a basic question that you could ask about manifolds and N is homotopy equivalent to N. So let me use this symbol to denote homotopy equivalence. N, can we deduce or can we say anything about whether or not N is homeomorphic to N? Or whether N is in fact maybe diffeomorphic to N, provided N and N were smooth. There are of course many variants. Okay, I mean, I guess that's not completely an absurd question. Potentially, you could imagine that understanding that two manifolds are homotopy equivalent is just easier to, you know, understand by means of algebraic topology. And if you just knew a general method of how you can decide that once you have this, they're also homeomorphic or diffeomorphic, at least then you know that maybe among certain homotopy types, there aren't so many actual homeomorphism types of manifolds. What this really lies you in practice is maybe something different, but okay, let's ask, or just ask, what can we say about such situations? And I mean, of course, we know many examples of this kind. So what do we know? What do we not know? So let's just go through this kinds of statements in terms of the dimensions of the manifold. So say the dimension is n, and suppose the dimension is 1. Well, then, okay, I don't know. In the first topology course, I hope everybody classifies. Maybe I should say M and N, which are closed manifolds. Let me only talk about manifolds which are closed, so compact and no boundary for now. So we certainly classify one-dimensional manifolds which are closed, and then the answer is yes to all. Answer is yes to all. They're homotopy equivalent, it just needs that. So in dimension 2, we have to work a little bit harder, but the same method works as well. Right? I mean, we still just classify all closed two manifolds called surfaces, and they're given by genus and orientability conditions, and all of those are, well, homotopy invariants, and well, then there is only one such manifold. So this is of course already, I mean, much more work in this case, but still known to be true. So now what do I want to say? So okay, I guess in dimension 3 the answer is already no. So dimension, sorry. Okay, dimension 3. So the answer is in general no. So I guess this is maybe also one of the first instances where we learn about such things are lens spaces. And I mean, again, let me not try to make indices correct, but there are lens spaces which are homotopy equivalent but not homeomorphic. I don't know, maybe L71 and then L73, or pick any other random number and then hope that we get it right. Okay, so lens spaces tell us that in general the answer to this question will be no, maybe not something terribly surprising. But so we can go on for the moment and ask, well, okay, then this question was just too naive. Let's be more specific about what do we know if we fix or if we take only relatively easy homotopy types of n. So
you have two questions, right? There's question homotopy equivalent, homomorphism, and homomorphism.
You can ask this question like this. Yes. Yes. I don't want to do that now, but yeah, that's right.
What all means.
Yes, all means both this and this are implied because for 1 and 2 manifolds, the classification implies that any topological 2 manifold is also canonically smooth. I mean, there's a unique smooth structure on each topological 2 manifold. Yeah, let me not get into that part though. So what about special m's? So I guess the most basic M manifold that we know is the sphere, and in that case, this question is a very prominent own conjecture called the Poincaré conjecture. So M is the M sphere, and this, and by this I mean this sort of question is the Poincaré conjecture. But asked if I have a manifold which is homotopy equivalent to the standard sphere, is it homeomorphic or maybe diffeomorphic to the standard sphere? So here the answer is, well, okay, so we have to think. So for homeomorphism, the answer is yes, except possibly, otherwise, the answer is yes. Right, okay, so let me come back to that. And for diffeomorphism, the answer is no. Okay, so in other words, if I have a manifold which is homotopy equivalent to Sn, then it is homeomorphic to Sn, but maybe it's not diffeomorphic to Sn. And so let me say what goes into these parts here. So the n equals 1 and 2 case, we already know, right? Because we know everything here. The n equals 3 case, that's, I don't know, this is a consequence of the geometrization conjecture. Of Thurston, which was essentially then proven by Paragon using Ritchie flow techniques. So the n equals 3 case is already super complicated. I mean, super complicated. It's already like a really deep theorem. And in this case, the homeomorphism and diffeomorphism questions are the same. There's again on each the 3 manifold a unique smooth structure, so there is no difference between these 2 questions. Now for n equals 4, this is a and okay, maybe just, I mean, to highlight the kind of fun that goes into these things. So I think Paragon was awarded a Fields Medal for it and didn't accept it. So I mean, this is like a big thing. And now n equals to 4, this is the result of Friedman's that I will get back to later as well. This was awarded the Fields Medal, and he did accept it. So essentially the fact that homotopy 4 spheres are homeomorphic to the 4 sphere, and it's open. Okay, so let me say this case is for homomorphism, and this question is open for diffeomorphisms. In fact, extremely little is known about such kinds of questions. Not a lot is known about such kinds of implications for smooth form manifolds. It's a quite complicated area. Then I'll get back to that as well. Okay, so but n equals to 4, we know this this Poincaré conjecture due to this complicated work of Friedman. And then in the n greater equals to 5 case, this is essentially proven by Smale using the so-called H-cobordism theorem. I mean, I should really say plus, potentially. It depends on how flexible you want to be about m and n itself only being possibly topological manifolds and not themselves smooth. So the question becomes easier if m and n are both smooth, and you just ask whether or not they're homeomorphic. Then the ordinary H-cobordism theorem for smooth manifolds that Smale proved will imply this Poincaré conjecture. Alrighty, so this is essentially what's known about homeomorphism stuff, and essentially the H-cobordism theorem plus more things also show that the question, this Poincaré conjecture for diffeomorphisms, is wrong in like extremely many cases. So there's this concept of exotic spheres. So those are exactly sigma homotopy equivalent to Sn. And by what we know before, in fact, those are sigma homomorphic to Sn. And one can essentially calculate the group of such things. So we observe that, well, maybe I should now insert oriented manifolds or something, but essentially this is a group by connected sum, right? You can take two manifolds, you connect sum them, and if both were homotopy spheres, then the connected sum is again a homotopy sphere. Turns out if you change the orientation, if things are orientable, which homotopy spheres are, if you fix the orientation, you connect sum with the reversed orientation, it becomes a standard sphere. So the collection of exotic spheres becomes a group called the group of exotic spheres, and Milner calculated this group up to an extension problem. Essentially, it's a finite group, whose order you can, I don't know, there's an easy part of it whose order you can calculate quite well, and there's a complicated part which is sort of controlled by stable homotopy groups of spheres. In any case, this is complicated, and I think, okay, so this group maybe let me denote this group theta n. So that's the group of sigma n homomorphic to Sn. And I think this is trivial if n is, well, 5 or 6. So it turns out there is no exotic 5 sphere, no exotic 6 sphere. There are exotic 7 spheres, open whether there are exotic 4 spheres. And then I think it turns out that there is no exotic 12 sphere. Don't know why that's the case. There's no exotic 61 sphere. And what I know for sure is that 61 is the last odd number for which there exists no exotic sphere. And I presume that, once you go higher, then there's always an exotic sphere, but I don't quite know for sure this. Smale also got a fields medal, and Müller also got a fields medal for this. Thanks. Huh? Yeah. This, I don't know, it's like the golden time of topology, right? In any case, so
all of them accepted.
Yeah, all of them accepted. But in any case, so I mainly wanted to say that whether or not you might be particularly interested in a question of this sort, the mathematics it has generated is quite rich, and I don't know, there are many aspects. I mean, the stuff that Friedman uses is very different from the stuff that Perelman uses. The sort of the high-dimensional approach that the H-cobordism theorem, Handel body decomposition, surgery theory generated are also sort of different flavors. So this really has questions of this sort have generated a lot of interesting mathematics, sort of independent of whether or not you actually care about the output. And in some sense, if I come to say about this paper I wrote with Anya, to me it's of a similar flavor. It's, the result is where you get something out. It's more the fact that you can prove it, which I find appealing than what exactly the result is. But in any case, so this is just a quick summary of what is maybe known for these exotic spheres. So let me maybe say a little bit about what about a little bit less special M. So maybe if M is only simply connected. Right. We had these counterexamples which were length spaces in dimension 3. Then we said, well, okay, maybe let's look at the easiest manifold we know, the sphere. Let's look at a little bit easier manifolds than length spaces, but still simply, not necessarily spheres, so simply connected manifolds. Well, then it turns out in dimension 3 we are done because any simply connected manifold turns out to be a sphere, right? By congruity, so we're good here. For n equals to 4, I'll come back to this in a moment. This is essentially what Friedman really did. So I mean, this was of course already spectacular, but Friedman proved much more than only the Poincare conjecture. I will write something down because it's sort of a nice mirror of. So what we do is in some sense a nice mirror of what Friedman did in terms of only the result that comes off of the techniques. This is much deeper. Okay, so in n equals 3 and n equals 4, it turns out that one can sort of classify manifolds, and if they're homotopy equivalent, they're homomorphic up to a small epsilon that I'll explain in a moment. And it turns out that just to give you an impression, for n equals 5, it turns out that such manifolds, so M5, are classified You can wonder what are the invariants, the algebraic topological invariants, a simply connected five manifold has. There is not so much that's there. So one thing that's certainly there is the second integral homology. That's certainly an invariant of your manifold. And then this manifold comes equipped with something that's called W2. So a simply connected manifold is always orientable, but it might or might not be spin. And then there's this second Stiefel-Whitney class, which tells me whether or not my manifold is spin or not. It's a homomorphism from the second integral homology group to C02. And well, this is a finitely generated group. So you can always write it as some finitely generated group H plus C mod 2 to the L, where this map is just the projection, the canonical projection, which takes away H and then just projects from C mod 2 to the L to C mod 2. And L is allowed to be infinity, and then we interpret this as just the integers. And you call this number L the height of your manifold M. And then, well, the group H2 together with its function to Z mod 2 and this height, this determines the diffeomorphism classes of simply connected five manifolds. So that's due to Martin. First try not to get a fused manifold. Right. Okay. So just that you get an impression, simply connected five manifolds, you can still do something. And then just to get another impression, in simply connected six manifolds were already killed. So here the answer is that there are infinitely many manifolds M, N, which are homotopy equivalent to CPN and to CP3, but MN is not homomorphic to M4. Okay, so I mean the easiest, one of the easiest simply connected six manifolds that is not the sphere is CP3, and then there are infinitely many such manifolds, all homotopy equivalent to CP3, but pairwise non-homomorphic. And I mean, then you can imagine, I don't know, you go up dimension, things just get worse. Essentially, you have no control over anything. But here you can still calculate it. Just because it's a fun fact, you all know that CP3 comes, I mean, it carries a canonical S1 bundle over it, right? Which is S7. And CP3 is the quotient of S7 by S1. And because, I mean, having a principal S1 bundle is something invariant under homotopy equivalence, you can ask what are the exotic 7 spheres that you can construct as principal S1 bundles over these exotic CP3s. And it turns out to be exactly half of the 28 exotic 7 spheres you can construct as these S1 bundles over CP3. So in other words, there's a lot of things you can concretely calculate. Alrighty, maybe just to get a little impression of things that are sort of known. So let me write down a theorem of Friedman more precisely, which tells you that you don't really need to start out with asking whether or not two manifolds are homotopy equivalent. And in fact, my understanding from the game that is usually nowadays played in the classification or stable classification of four manifolds is that you don't really want to start out with assuming two things are homotopy equivalent, but rather you want to say that certain algebraically looking invariants you associate to them are already equivalent. Often this is implied by homotopy equivalence. And once you have this, you want to deduce that they're homomorphic or Escobar or something like that. So Friedman tells you the following. It says that if you take the unimodular form over Z, so just the symmetric bilinear unimodular form over the integers, then 1, if lambda is odd, or no, if it's even, and by even I just mean it's a symmetric bilinear form. If you evaluate it on the diagonal, it's supposed to give you an even integer. Okay, you call the form even if it has that property, you call it odd if it doesn't have this property. So if it's even, then there is exactly one homeomorphism type. And lambda whose intersection form on middle dimensional homology is lambda. Okay, so every simply connected. This is connected. Okay, Okay, so every simply connected form manifold has this nice unimodular form on the middle dimensional homology, just by Poincare duality. And that's going to be a unimodular form over Z. And Friedman tells you, well, once you have an even form, any such even form is realized by precisely one homomorphism type of a manifold. And the second statement is that if lambda is on, not even, there are two non-homomorphic but homotopy equivalent such manifolds. I'd like to write it with n lambda and star of n lambda, because the star is usually referred to as the star partner of m lambda, both realizing this form with lambda being the intersection form of m lambda, and characterized by somehow. I mean, how will you distinguish those two? It turns out this one is not smoothable. It does not carry a smooth structure, but m lambda does. Okay, so this is a very tight connection in simply connected form manifolds between algebra or forms and just the homeomorphism types of manifolds that arise, up to this issue that if your form is odd, there will be two manifolds due to this fact that, well, there's going to be one smoothable one and one non-smoothable one. Let's just highlight this. Also, to explain that things of this kind are not super ridiculous. For instance, the star partner of CP2 is quite concrete. I don't know. I always forget exactly how this works, but essentially you can embed I don't know, the trapole knot in some particular homology 3 sphere, and you do surgery on that knot. And you get something out. The fact that this trapole knot had art invariant 1 or something will allow you to prove that the output of the surgery is not going to be smoothable. But yeah, in some sense, at least some of these star partners are still more or less concretely given. The question is how can you perform the surgery precisely? Okay, so this is what Friedman tells us. In particular, he tells us that any form arises as the intersection form of a form manifold, I mean unimodular one. And just again to tell you that. Okay, so I do want to take a little bit of time and highlight the difference between the question whether or not things are homeomorphic or diffeomorphic. So Friedman tells us that every form is realized by a topological manifold, and I mean in an essentially unique way, up to this funny business that potentially there might be a second one.
What is it also? Isn't there also an issue with triangle, whether they're triangulizable?
Yes, that's a good question. So the invariant which distinguishes those two is called the Kirby-Siebmann invariant. It is a priori an invariant which depends only on the tangential homotopy type of M, or I mean the tangential information. So it asks whether or not the stable tangent bundle lifts to a PL bundle. But what is not true is that if this is the case, your manifold also has a PL structure. Right? This is something that's called smoothing theory, and from top to PL manifold, smoothing theory works only in dimensions different from 4. It's just not true that a form manifold which has not trivial Kirby-Siebmann invariant will have a PL structure. A good example is if you take the E8 manifold that comes from this term and you connect it some with itself. Right, the E8 manifold will have Kirby-Siebmann invariant 1. If you connect some with itself, you add those two ones. It's an invariant in Sigma 2, it becomes 0. But what I'm about to write down will tell you that this connected sum is not smoothable. There is also a different question just about triangulations, not necessarily PL triangulations. And conjecture about this was disproved by Ciprian and Manolescu using tools from what I'm going to write down now. So let me say that here's the theorem of Donaldson. Okay, so yeah, so that was a fused medal. Here's another fused medal in the same year. Donaldson proved that if lambda is even, or maybe I should say if lambda is positive definite, only the form 1, 1, 1, 1 is realized. I mean plus minus, I should say. Only this is realized by a smooth manifold. What? No, it's just in the positive definite case. I mean, this form is not even. It's just among, yes, I mean, the statement is among even forms, no positive definite form is realized by a smooth manifold.
Right, we are in.
No, I mean, it's just in general. Yes, yeah. And actually, I've heard the story. I don't know if anybody's watching and knows this is wrong what I'm saying. I've heard the story that Donaldson proved this theorem using gauge theoretic methods. So I don't know. You study certain nonlinear differential equations on your manifold. You study the space of solutions, and it has a certain type of geometry. You construct. I don't know. It's a beautiful argument. And then he figured out this argument, but it turned out he didn't know so much about forms. So he was like, I mean, have I proved something good or not? And so he went to an office mate or like a colleague down the floor and asked, like, are there many like definite forms which are not standard? They were like, yes, all of them. I don't know. It's like millions of them around. Many forms. I mean, many forms. For each fixed rank, there is a finite amount of positive definite forms, but the amount sort of grows. There's tons of them. So this is a huge difference. It tells us topologically everything is realized essentially uniquely, smoothly, not everything is realized. And the next part, which is just a fact that I don't really know who to contribute to. There is not one four manifold closed again. Let me say closed, where one knows, I mean, whatever that means, also the structure. So there are closed form manifolds known, smooth form manifolds, where we know that there are many different smooth structures, but there is not one known where we know all of them. And I mean, of course, most prominently, we don't know if there is an exotic force sphere, but also to make it concrete, there are certain types of complex surfaces called Dolga-Chet surfaces, which turn out to be all homeomorphic. You can prove this using this result, but you can use Seiberg-Witten theory, again, sort of nonlinear differential equation theory to prove that they are not diffeomorphic. So essentially here the point is not everything is realized, and if it's realized, we essentially don't really know by how many, and things are much more.
We also don't know if they're, I mean, if, like, just if they're for instance uncounted.
No, I think on closed manifolds there are at most countable many. Yeah.
But okay, so
but
okay, so
on open manifold,
but we don't know like if there could be. It could be that every one of them had infinitely many.
Yes.
That could be.
Yes.
We don't know if there's a need for infinitely many on the force sphere.
Yes, I mean, this is what I mean when I say there's not one form manifold known where we actually know what's happening.
Right.
Anything could be true.
There are a lot of manifolds where people have shown that they're infinitely many smooth structures,
Yes.
right?
Yes.
So that is known there.
Yes, we've already.
That's sort of a kind of that, right? That you have infinitely many.
Yes.
So
You know something, but you still don't know that those are all
right.
Yeah, but you're right. I mean, there are examples where we know that there are different smooth structures, even infinitely many so. But yeah.
But some people even conjecture like that any smooth form manifold has
infinite. Yeah.
Infinite.
Yeah. I mean, I don't know how one could possibly conjecture that, but yeah. It just seems to me that one knows nothing essentially. And but yes, you're right. I mean, I think the point is one knows nothing in general, but anything could happen in principle.
That's the thing where they have like these, they take the CPU2s and CPU2 bars, and then they take connected sum, and then they prove this is not of all right.
No, it's all good. I mean, yeah, okay. I mean, I did want to highlight the fact that smooth form manifolds are much more complicated, and also the methods that go into proving things like this are very different from this stuff. This is really delicate points in topology. This is, as a topologist, I'm allowed to say really delicate analysis. This is really gauge theory. You study differential equations and solutions of differential equations and try to understand the moduli space of such. It's very different things. All righty, maybe I should also, how much time do I have? Okay, good. How much is not so much? Okay, 3 minutes. So let me say that, okay, I apologize. So let me say that one more thing is known. If you stick to certain kinds of manifolds, namely hyperbolic manifolds. So manifolds which admit a metric of constant negative curvature, then it's a theorem of Mostov that any two things which are homotopy equivalent, in fact, are isometric. There's an isometry between the two. And this led Borel to conjecture that this is true for things that homotopically look like a hyperbolic manifold. And what is the key property of a hyperbolic manifold? Well, its universal cover is hyperbolic space, which is contractible. And so Borel conjectured that whenever you have a manifold whose universal cover is contractible, then if you have two such and they're homotopy equivalent, they should be homeomorphic. Okay, so then I'll just write down the theorem that down here, and I apologize for not explaining more about it, but I'd be happy to do so if anybody ever wants to actually do it. So this is, but I actually can look it up because it's technical. So what is the theorem? Okay, so we have to have some assumptions. So we have to take pi is what I call a four-dimensional Poincare duality group. So essentially think of pi as the fundamental group of an aspherical four manifold, and aspherical means this universal cover is contractible. I don't know, you could look at surface bundles over surfaces, which where both surfaces have genus at least one. Or I don't know, you can look at circle bundles over aspherical, like irreducible free manifolds. I don't know. There are examples of such objects. So then we have to do a technical assumption. So we have to assume that pi satisfies all the Faraday-Jones conjectures. There is not a single group known for which this is not the case. I think if you do, you probably don't get a Fields medal, but this would be the probably most spectacular thing people have done about the Faraday-Jones conjectures in maybe say the past at least 8 years, I would suppose. So it's been proven for many groups. It would be good to find a counterexample. It shouldn't be true, but in any case, so assume that this satisfies the Faraday-Jones conjecture, and assume given manifolds n and n, so we're closed four manifolds with pi 1n and pi 1n being just that group. And okay, now we have to make one further assumption, which says that, well, whenever you have a manifold with fundamental group pi, there's a classifying map to E pi, which is an isomorphism on pi 1. So maybe call it Cm and Cn. And you have to assume that they have degree plus minus 1, which makes sense because pi is a four-dimensional PD group. So in an appropriate sense, its top homology is the integers. So is that of m and n. You can ask whether or not the classifying map has degree 1. And if this is so, then the following two conditions are equivalent. So one is that m and n are as coordinate, which under further assumptions on pi, so pi is good in the sense of Friedman, this will imply that m and n are homeomorphic. But yeah, that's just something that we will do. And the second condition is that the intersection forms are isomorphic, and the Kirby-Zeeman invariants agree. Agree. And yeah, under certain assumptions on M and N, if both of their universal covers are spin manifolds, then you can get rid of this assumption. It's automatic. But in any case, the theorem says something like, under appropriate assumptions, which are still satisfied in a non-empty set of examples, you can show that M and N are as coordinate, almost homeomorphic, if and only if their intersection forms are isomorphic. Okay, so let me stop here. Sorry.
We don't have much time, but before we always have time for at least the question. Yes.
Yeah, okay, so in general, I should say that there are two different ways of trying to prove results of that sort. One is classical surgery theory, and the advantage of classical surgery theory is that much is known about it, and you can use good tools. The disadvantage is that you have to start out with a situation where you already know that M and N are homomorphic, essentially, as you're more or less one. Turns out, under these assumptions, it is known that M and N are homomorphic by like a concrete argument using cell decompositions of M and N, and fill your way around. So we now have taken the path of taking this for granted, they're homotopy equivalent, and then running a general surgery theoretic argument. In principle, there is a second way of dealing with these things, which builds on a modified version of surgery theory invented by Craig, which starts out not with a situation where you assume M and N are homotopy equivalent, but where you only know that certain part of tangential data are equivalent. So that what's technically called is they have equivalent normal K types for some K. And in this case, one can also run this modified argument to give a proof of this fact. And maybe that's one way I can motivate this condition that these things have degree plus minus 1. I mean, it appears in the proof at many places. But this condition essentially says that pi 2 of these manifolds viewed as modules over pi 1 are finitely generated projective modules, which implies that some equivariant K invariant of these things are 0. And this simplifies massively the calculation that we would have to do in the Craig modified surgery approach to proving that under these conditions you find an S-cobordism. But I mean, all of it is you start out, you produce some cobordism, and then you do surgery theoretic methods on that type dimensional cobordism to show that it's, can be manipulated to being an S-cobordism.
All right, I think we should stop here. Thanks a lot, Markus.